right, so this example is basically the same as the example before, but we've got data that's been sampled every second instead of every 2 seconds. And so what I've done is plotted the points, and I've drawn the rectangles representing my left-hand sums, right? And then I've computed the left-hand sum. All right, so I got 371 feet. And then I also drew the rectangles that represent the right-hand sums. Now I didn't continue the rectangles all the way to the bottom. But if I just take, well, let me mark on here. So the left-hand sum is basically that you're taking the first 10 left-hand data points, right? And adding them up and multiplying times the width of each sub interval. And then for the right-hand sum, you're just going to take all of the right-hand data points, right? And multiply times the width of the subinterval. Okay, and in this case, delta t is equal to 1, right? And we have n equals 10 intervals. Okay, so let's take a look at the error again. Now, all I've done is basically tried to copy these rectangles over. So, this rectangle is represented here. It's the difference between the upper estimate and the lower estimate. Okay, so in this case, because it's, again, an increasing function, the right-hand sum is an overestimate because the right-hand data point is always higher than the left-hand data point. Okay, so our error band, essentially the difference between the right and left-hand sums, are then represented by these the stack of rectangles. And the height of that stack is the difference between the maximum value at the last interval at 50, or this value of 50 at 10 seconds, and the left hand, the first value at t0, right? So we have a difference here of, this is basically 30 feet per second, okay, times 1 second, okay? So that gives us a difference of 30 feet, right? So our estimates essentially give us values that come within 30 feet of the actual value, right? Because we don't really know where in that band the actual velocity is. So, and you can see the same thing down here. The difference here is 30 feet, right? Now, what's interesting is that, okay, we cut the frequency of the sampling rate. We cut the time in half, so we doubled the sampling rate. Right, and we have the error. We have this difference between the upper and lower estimates. And so, so one question that you're going to be asked in some of the, I think it's one of the discussion questions, maybe even a homework problem, is how frequently must we record the data in order to estimate the distance within 0.01 feet? All right, so let's think about that question. And if we look at this stack of our error here, it gives you a good clue, because essentially that stack is the height of that stack is never going to change. You're going to start out at 20 and you're going to end at 50, and so the height of the stack is not going to change, but the width is going to change if we sample more frequently. So let's try to figure out what our delta t has to be. So basically, we're going to take our delta t under whatever the sampling frequency is, and we're going to take the difference between the upper and lower values of the function, and we want that to be 0.1 feet, right? So we can find delta t just by dividing both sides by 30. So we get 0.1 over 30, which is 0.00333 seconds. Okay, and the units are in seconds because obviously the distances or the velocities were in feet per second and our times are in seconds. So this is So we would have to sample the velocity every 0.00333 seconds in order to get the estimate to be within 1/10 of a foot. Okay, so again, like I said, these Riemann sums are the basis for the integral. And the idea is that if you sample more and more frequently, that essentially you get the exact area under the curve. Okay, so here we're showing, it's basically the same velocity data that we just had in those last two examples. We're just sampling here with n equals 20. So we have 20 subintervals. Here n equals 40, so we have 40 subintervals. And if we let n go to infinity, then essentially the idea is that you get the exact area under the curve. Okay? So, and if velocity is positive, the total distance traveled is the area under the curve. Okay, so it's if velocity is positive. We're going to talk about what happens if velocity is negative here, because velocity, remember, velocity is a vector. Velocity has direction as opposed to speed, which does not. And when we're dealing with linear motion, we're going to use the negative sign to indicate direction. So positive velocity would be in however we define positive velocity from positive distance from the whatever our frame of reference is, and negative would be in the opposite direction. So, okay. I'm going to have you, let's see what's coming next. So example 4. All right. So we're going to talk about negative velocity in example 4. So I'll meet you there.